Hello, everyone, and welcome to Handmade Hero, show where we code a complete game live on stream. Let's go ahead and take a look. We were doing lighting last weekend, and I think we have, I want to say we actually made some good progress. We just did some tight fitting of the actual sort of lighting bounds to where we were actually looking. So basically, all we really did, we didn't even optimize it at all. All we did is just fit the lighting bounds to the total viewable area more accurately. And I believe you can actually see, if I pull out, you can sort of see what's happening here. So only like the region that was actually visible, plus a little like apron so that we make sure you don't see it kind of page in the lighting, because the lighting needs 10 frames of startup time or so, something along those lines, right? You can see it kind of just like follows you around pretty carefully now. And so when you're actually in the game, we more or less got rid of any weird lighting anomalies that were due to the fact that we're not properly aligning the visual region. And we also improved the speed dramatically, because we could use at this point we can use a much tighter bound on the lighting region, which means a lot less lighting samples have to get sent out. And again, that really helps us keep the frame rate up. So even though we've done like literally no work to optimize our full cast here, we've already gotten our speed within striking distance of 30 frames a second, which is pretty great, because that just makes our workload that much easier. It gives us a running start, if you will, towards making the lighting be something that we don't have to worry too much about. And again, we haven't even put it on the GPU or anything. This is actually just running entirely CPU side. So we can probably start, I think, to upgrade the lighting Raycaster now to try and make it a little bit faster. And I'd like to do that today and tomorrow. And we'll see how far we can get with that. But then I think our last big push is going to have to be working on the lighting equations and perhaps some tone mapping to get the lighting looking really good. It already looks okay, but you can see there's some rectangular interpolation that still kind of is in there I don't like. I'd like to fuzz that out a little bit more. The actual bounce equations and what we're putting in for reflectors isn't actually right at the moment. So we want to kind of clean that up. We want to put in reflectors for large objects like trees, for example, too, so that those collect light. Right now, they're not collecting any light. There should be some light reflecting off of here and onto the ground and that sort of stuff. And that's really just a world gen issue, so that we can control what we're pushing down there. So a lot of things like that is then a quality pass on the lighting. But for right now, what I'd like to do is, again, focus on that bottom line number. So I'd like to focus on getting this full cast down. And what I'd like to do is basically say, look, let's try to get it down to like 60 frames a second on like a beefy machine like this one. This machine isn't like the fastest machine out there or anything, but it's a pretty fast machine. So I'd like it to run at 60 frames a second so that worse machines, like machines that aren't as good as this one, could run the game at a reasonable 30 frames a second. Just as a baseline there. And again, another thing is you can also drop the resolution down a little bit too, but that won't help the lighting particularly. We could drop the resolution of the lighting down, obviously, as well, and that would help it, but I don't know that we really want to go that route. So what I want to do today is just look at what we've got for that lighting routine, and I want to go ahead and in Handmade PRJ here, I want to go ahead and look what we've... What? What was that about? Did I not switch projects? Oh, I didn't switch projects. Sorry. So I'm going to go ahead and switch projects there to Handmade Hero. Just go ahead and run the build. I'm going to jump over to the lighting. And what I want to do is we just want to start looking again and refamiliarize ourselves with what we're doing in the Raycast. Take some statistics. I believe we had a little lighting statistics dump. And I don't know that we're still drawing that, but what we should do is re-enable that. In case we don't have it. Oh, actually we do. So you can see here we have a bunch of information. Now, I think now is a good time to say, look, lighting probes are out. We're just not going to use them because we've gotten really good baseline example running with no light probes. And that'll save me a bunch of code. So maybe the first thing that we'll do... Oh, That's nice. Maybe the first thing we'll do is just pull that out completely because we're done with that. I'm just not going to try and do it. We're going to accept whatever quality we can do without them because it looks like using the voxel directly is just better, right? It's simpler, and we know that we're always aligned. So let me go ahead and pull that out of everywhere that it existed. So for example, in the world, we had this notion here of light probe slots, and this was just a huge pain in the butt. And what I want to do is get rid of that entirely. So everywhere we were doing light probe assignment is just going to go away. So it just makes it easier for us to work with. So everywhere we were doing like an is light probe, that sort of thing, that's just going to get out of here entirely. And so this idea of assigning indices and removing indices can just go away. And so again, just really simplifies our code and gets rid of an entire unnecessary pass. And which could cause like, bugs as well, because there's this whole other thing that had to happen properly. And so again, it just simplifying the entity system, getting rid of stuff that we don't need, that was just, we thought we needed to try it, and then we tried it and it turns out it wasn't really necessary. So at that point, I don't want to leave it lying around because it's way better if we just don't have it. So let's go ahead and keep going with this. Just pull all of this stuff out of there. You can see that we had a few places where that was sort of tied in. And I'm just going to get rid of any place that was talking about that because we just don't need it anymore. Let's go ahead and take a look. There's our light probe index check to actually push the light probes on. And we can get rid of those now. And I believe that also means that the entire push light probe system there can go away as well. So basically here's the thing though, I might leave global lighting show probes in there because we actually could still draw the voxel. And so that might still be worth it at some point. So maybe I'll leave the control in there and we can try to wire that up at some point if we are so inclined. So I'm going to go ahead and get rid of any more mentions of the lighting here. And I'm also going to get rid of push light probe, this code right here. So this whole thing where we've got commands light probe position, again, going to go ahead and nerf all of that stuff. So every place that was previously using like light probe buffer and all that stuff, again, just really making it easier to, just getting rid of complexity in the code and making the code more flexible as well, because now you don't have to worry about a light limit or anything like that, a light probe limit. You just get the lighting that is the voxel and off you go. So I think that's great, and I'm psyched about that. Again, just really helps us in a lot of places. So let's go ahead and get rid of any mention of these light probes, just so they're gone. This is great. It takes out a lot of ugly code that really we just didn't want to have, right? There's no reason for it. We don't actually want that. Where was that coming from? Max light probe count. I don't even know where that's specified. Maybe we already got rid of it. So anyway, create world. Yeah, you could see this was getting like passed through a bunch of people, which again, so really nice that it goes away, because it's just nasty. It's just ugly, and there's no point to it. So I'm also gonna search for light probe here, and I'm gonna go ahead and just look to see if there's anywhere where we're still doing that, and try to get rid of that. So there's some, here's an is light probe call. Gonna get rid of that. Looks like there's a brain light probe. I'll get that on the second pass through. Here's some light probes that we're adding here. Let's get rid of that because we don't want those. Let's get rid of these light probe positions. Let's get rid of these add light probes. And now I'm also going to do a search for light underscore probe, just so we can see anywhere that was doing. We're going to get rid of the light probe counter and the light probe brain. So that pulls light probes out of the system entirely, and now we don't do any of that bookkeeping or any of that work, and we just get the exact same result, right? And that's really great because I don't really want to have to deal with any of that stuff, right? It's just extra work that I don't want to do. So you can see here what we're doing in the sort of in the, I don't know how to look at this, but if you look at the costs here, there's a lot of stuff now that I think that we want to start working our way through to simplify this code. And so what I might do to start with today, before actually trying to optimize it, I might just try to simplify it. So in other words, it's been through a lot. We've done so many experiments with lighting, trying to figure out like a good system, and we finally kind of, I think, got to a place where I'm really happy with how it's turning out. So I'm ready to start turning the crank on it. And I think this is actually like something we can ship, right? So what I want to do is say, can we go through here and simplify everything that's happening so that we're down to like the bare minimum of stuff so we can focus on just what we need. And so, before looking at these numbers, and I'm glad that I have them now, before looking at these numbers, what I want to do is go and, for example, probably change the way that we're generating like our sphere tests and stuff like that. And the reason I want to change that is because if you look at how we're picking our ray directions, we were picking our ray directions before we knew about our octahedral map, right? So we didn't actually have an octahedral map when we did our light relaxation stuff. And I think probably, at least my guess is, that now that we know that we're doing an octahedral map and it's 8x8, we might just want to say, look, we do 64 raycasts per light probe or something. And that's just how it goes. We send one out of each texel each time or something like that, right? And then what we would know is when we load up the rays, we could load them up in such a way that we know we're loading up a specific like set that gets used exactly in a specific way, right? So we could actually make so we don't have to do like, oh, where in the octahedral map is this ray, or let's make sure that these are evenly distributed across the sphere, because we know like each time we're just updating one of our octahedral positions, and we know which one it is because it's always the same one since the probes don't rotate, right? So I think I'd like to kind of go through and start that process. And again, just to simplify sort of the way that full cast process is working. So if we go into the lighting system and I go to the full cast, you can see the function here that we're talking about. And what I mean to say is, so you can see here, we do our ray bundle count, right? And I think our ray bundle count, I think we actually are doing 64 casts currently. I'm not sure, so let's go ahead and print that out in the actual system here. So if we want to, we can actually print out our array bundle count because we know the array bundle count is always equal to the array count of, like, it's this value, right? So when we actually do the dump at the end where we print out our statistics, which is right here, what I can do here is say like rays per probe or something like this, right? I can go ahead and compute that by saying that the ray bundle count is, it's just going to be 4 because that's how many is in each bundle times however big the sampling sphere is, right? And the sampling sphere, I think, is just in the solution, if I'm not mistaken. So, like, the sampling sphere, excuse me, is just one of these things. So I should be able to say, like, all right, like, you know, that. So however many there are, oops, in there, and off we go. Okay. So if I take a look at what that's printing out there, our rays per probe currently says 72. So basically, I pretty much want that value, I think, to be 64. So each frame, I want to send out 64 arrays, one out of each of the 8x8 voxels. And I think that's basically what I want to do. So that's effectively going to be a stratified sampling. And we can just generate like lots of like sort of fairly even coverages in there. Now, one thing I don't know is if we did a stratified sampling so that we're basically just always casting out of a particular piece of the octagon there, of the octagonal map. What I don't exactly know is I don't exactly know how the rays should be distributed inside that stratified sample. So from frame to frame, I don't actually know if what we want to do is just pure white noise out of each individual voxel, each individual texel, or whether we still want blue noise out of each individual texel, because my gut says blue noise, but since it's already confined to the bounds of the voxel itself, I'm not sure what that actually means. And I mean, I guess what I would think, gosh, I guess my thinking there is like, you want blue noise over the sphere, and then you want to bucket the blue noise into like, you want like something that's blue noise, but constrained so that each one is only in the texel of the octahedral map. And I'm not sure exactly how to get that, right? That seems kind of confusing. So maybe, I don't know, maybe we'll start with some randomness. Like maybe we'll start with just white noise, and we'll try to figure out how to work with that later as we go. Because I really, like, I in my brain, I'm not coming upon, like, the instant answer to how we would want those sampling spheres to go. We know that, like, we want to modify the sampling sphere slightly from what it actually is right now. So if you look at, like, the sampling spheres, you can see that there's a sample direction that's like, here's how many of these bundles per sphere there are. And in this case, like, 18 is not what we want. We want less, if we're doing 4 times this number, then we want this to be 16 so that we have 64 of them. Oh, looks like we already computed this value too. So, what I want to do is I want to, in addition to this, also have which indices you write into with each of the results here, right? So what I want to do is inside the full cast, you can see that when it goes to update the voxel, it has to do the get octahedral offset for the incoming light direction. But I don't actually want to do that. I want to be able to just sort of sum the voxel directly, right? So I almost don't even want to do it this way. I want to just, and I don't even want it to be random access. I want to basically just do a thing where I like load up whatever was currently in the texels, do the raycast, and add it back, right? So it's like it's a very straightforward procedure, that I want to be able to do there. So yeah, so I think what I want is this would change a little bit, and what we would actually do here is we'd actually just go ahead and walk the texels. So in much the same way that we were previously doing like our weight updates here, like this sort of stuff, right? It would be more or less this sort of code. So in here we would say like, let's walk the texels that we're looking at, right? And for each one of those, in the thing we're actually updating, and in this case, it's going to be the spec atlas, not the diffuse atlas. So for each one of these, I'm then going to go ahead and get like the, I'm going to go ahead and do 2 raycasts, right? And so instead of ray bundles, we'd actually do this, right? So we'd step through the spec atlas tile each time. We would go ahead and keep the ray bundle index as something that just kind of increments along, right? And, you know, we don't even really need it. We could just reconstruct it from the TX4TY, right? So we could do that too, but we'll look at that in a second. We do the raycast, we update the voxels, but here, instead of like doing this stuff where the update voxel call was, we can actually just grab this directly and do it to the texel in question, right? So because we'd already know what this is. So it would be something like, you know, like this. And we wouldn't even really need this part of it. And we could probably step that texel, yeah, more directly. So basically, the tupdate blend, I think I would just say, is a variable we pull out at the top. And, oops. And we know that we've got like the transfer PPS here. And that's it. So it'd be something like this, where we just always know what the desk texel is because we just have that information, right? And so, you know, it would just be this. Probably. Again, we probably want to do this a little bit more cleanly because this is not the best. But something like that. And then what we would require is that for each of these, when we pull out this ray bundle, we want each ray direction for the sphere to know that it goes out that particular texel, right? So then when we go through our subrays, again, we know that each subray should go by 4, actually. So in this particular case, I guess I take it back that, because, yeah, we would want to do that right as 4 writes as well. So really, like, you'd probably want to pack that down. Anyway, So, yeah, here's what I'd say about this. I think we want to do this even more explicitly because if we know that we've got a bundle of 4 rays that we cast, that's 4 different texels we can update, right, at the same time. And so really all we need to do is make a v34x here that's our transfer PPS, right? And so instead of doing that each time, what we would do here instead is in the slow part here, the part that's non-SIMD'd, we would grab the transfer PPS for each one of our subrays, like this. You know what I'm saying? And then the update could happen fully wide. Like, we don't actually need the update to do anything slowly. Because we know we're doing 4 times 3. We know we're doing 12 adds here. And those can be done entirely linearly. Like, entirely SIMD'd, right? So what we would want to do is, like, load all the stuff up and romp all the stuff out. You know what I'm saying? And so let's go ahead and structure the loop more that way. I think that's just better. So in here, like where we were previously doing our sort of updates, right? So I think what we want to do is something more like this. So, you know, here you can see us pulling out these spec texel sets, and what we want to do is just update those spec texel sets, right? So we want to be able to just load the t-update blend in there and then romp the blend. So it's just going to be like a replicated t-update blend, and then we're just going to go ahead and do it fully wide. So I think what we want is literally this. Like, we want exactly this load behavior here. And so we can actually, I think, just copy this. So I think maybe I started with like sort of the wrong template loop. So maybe let's just not do that. Let's do this instead, like this, where we load each of these up, right? Like this. And so what I want to do here is say, let's do the loads, then let's do the stores, and write them back. You know what I'm saying? And looking at that, we probably only want to do 4 of these at a time, which would be 3. Because we probably don't want to do 8 wide raycasting, although we could, and that would also probably allow, well, yeah, maybe we do want to do that. So another way to look at that would, yeah, be like, look, don't do this, just do this one loop of Y. I kind of like the sound of that. So if we just did one loop of Y, and then we just pulled out 2 ray directions, did 2 ray casts, and then wrote everything back. That seems better because, again, if we wanted to switch to AVX eventually, you'd want the 8 wide path to happen here. So I'm actually fine with that. So what we want to do here is we want to do a store F32 4x. You know, so what we'd want to do here is basically this. So after we like update these variables, which we have to do, we would want to do a store, which I assume we have. No. So we have a load F32x, but we don't have a store F32x, so we're going to have to add that guy. So there's that address, and we just want to know like what's the actual F32 4x that we have. And that's just going to be a store U. And it's literally just going to be like whatever this a.p value is, right? All right. So if I want to do a store there, these would just be store F32x. I'm going to get rid of this. And we would basically like look right S0 back to the 0 location and so on, right? So it'd just be something like this. right? So we do a loads, we do stores. So at the end, after we update everything, so like after the lerps, we would just do the stores. And the lerps in this case, I think we could just do, yeah, I mean, I think we could just do this as like, you know, S0 equals lerp from S0 to whatever the transfer PPS was, kind of a thing. The problem we're going to have here is that when we've loaded these up, right, it's RGB-R, GB-RG, right? So these are like strided across. So the transfer PPSs that we get are actually going to have to be strided in the same way, right? Like we're going to have to actually have those come across lined up. So, you know, it's going to be something like this. You know what I'm saying to you? Which makes it a little bit harder for us to work with. But that's how it has to be packed to do the load, to do the storage eventually. So we're going to have to make sure that we put things in here correctly. And again, I'm not really sure how we want to do that. We might do that the cheesy way first. And then, you know, because the cheesy way to do it would just be like, look, we've got, you know, a certain number of F32s here. And then what we're going to do in each of these cases is just, we're going to just load up out of that. So, you know, it'd be this. Right? You'd go through and load them up, and then you would load out of that array to get your transfer PPS like so, right? So, you know, you just do that. And here's that transfer PPS. And that's going to load, you know, 6 times 4 values, which is how many this would have to have in it, right? So here's the RGB. We know that, sorry, it's 8 of these, right? So 3 times 8 is the same as 6 times 4, so that would load correctly across the top. This tupdate blend, now we need to be able to do this wide, and again, that's not particularly difficult. So what we do here is we'd make our, basically our blend value and our inverse blend value. So we'd have our blend and our inv blend, right? And this would just be load F32. I guess I don't know. Load F32. This. So this would just be something where we, you know, replicate the value across. So in this case, we'd have a blend and an inverse blend. And the inverse blend is just, you know, 1.0 minus the blend value. So in order to do our lerp, it's pretty simple. So for each of these, it's just going to be like blend times the T0 plus, I'm sorry, inv blend times the T0 plus blend times no, sorry, it was S0. So T update blend. I don't know what T update blend actually represented, so let me just make sure we've got that right. T update blend. All right. So T update blend is how much we're going towards. So that means the inverse blend should be on whatever the old value was, which is that, and the new value should get the T0, right? So that's the entirety of our update, right? 1, 2, 3, 4, 5. And so that updates our sort of lighting template there. And I think this would do everything that we needed, right? Now, this will not be correct because we haven't changed our spheres to be sorted the way that I just said, right? So it's not actually correct. Let me go ahead and say, oh, also this spec atlas here, we don't actually want offset from texel for spec tile probably. Oh, well, actually, maybe we do. It's just tile, right? So, so I think that's what we would need here. So when we go through and we're trying to set up our PPS here, we now have like sort of a double loop if we do want to load all of these at once 8 wide. where we basically say like, okay, we're doing a raycast. Here's our, our raycast. It's only going to return 4 things, rather than 8. And like I said, we may want to go ahead and start just doing it 8 wide. The problem we would have here too is I don't actually know if we want to split this into 2 halves. Because the other thing that's a little bit ugly is when we do our raycasts, we probably want to do the raycast 4. We want those 4 to be as close as possible. And if we actually raycast 4 in a row, those are going to be spread out more than if we did 4 like right in a little square pattern, right? So that part's kind of annoying, and that's just because, again, the hierarchy, what you load out of the hierarchy is different. And so it's hard to say. Usually if you trace ray bundles that are near each other, I mean, that's usually more coherent, but, you can't really guarantee it. So it's hard to say. But anyway, if we were to do it this way, then we would essentially do 2 raycasts, right? And then we would do this for each of the raycasts. So, for example, when we're pulling out the sub-rays here and we're doing like the get component calls and all this garbage, what we need to be able to do here is actually have this code be sort of usable if we're going to do 8 of these. And the only thing that I would say here is I'm not sure... I'm not sure if that shouldn't maybe be done. Let me take a look here. I'm not sure if maybe that shouldn't just be done at the end of this routine. You know what I'm saying? Because rather than return this information back, it seems like you would just want to have this be handled rather than returning the result this way. Because since we don't ever do a raycast for any other reason, you might as well just compute the diffuse irradiance right there, right? And just allow the optimizer to see more stuff. So I'm not actually sure that that is the right thing to do there either, because it seems like it's kind of just wasting effort to a certain degree. And again, that way it wouldn't have to return anything. It would just literally return the emission information. And that seems maybe better to me. Yeah. That seems maybe better. So, so I actually don't know if maybe this should just be welded right in here. You know what I'm saying? Where basically we're just saying, we just have the transfer is what gets computed here. So that all can be welded together. So when it does that raycast, you get back the transmission that you want, and then the outer code can do the blend for you. That seems more sane to me, probably. Yeah. So I'm going to go ahead and say that's what we're going to do here. And I'll go ahead and throw this debug code in here as well, like so. Just because I don't know if we're going to need that someday, but we'll leave it in there in case we need it. So this is more what I'd like this to look like. We just loop over, just going over each one. And then, I won't even bother with the transfer PPS here. What we'll say is that raycast result, we just get back a transmission, right? Maybe something like... Sorry, I'm just trying to think this through what I want here, but I think I do want just this. So, it's just this stuff doesn't really get used that way anymore. I guess what I'm thinking is maybe you just give it... I mean, another way to do this would be we don't even do that. We just weld this whole thing in. You know what I mean? The reason the Raycaster is separate at the moment is because I like to be able to call it for debug purposes, you know? But it may be that it just wants to work on the size of a tile anyway, and this stuff just gets welded in. So it's like you just sample a sphere. That's just what happens. You know what I mean? We don't care about ray weight or any of this stuff. Yeah. I'm thinking that's might be what I want. Actually. So if that were the case, here's what that would look like. Essentially, you would pass the Raycast routine here. And I don't know what debugging was doing. Looks like it pushed the debug box on there, yeah. So essentially what you do is you tell the Raycast routine, and the Raycast routine would not return things. So that's out of here, right? So Raycast result just kind of goes away. And so then what you would do is you'd say the Raycast routine, you actually tell the Raycast routine what to update, and the Raycast just does the update in place, right? So essentially, you know, you don't get to just get Ray information back. Instead, what happens is it does the load and store, and you just give it like, here's the Ray bundle and here's the Texel to update, and it would do like this code. Right? So at the opening, you know, it would do this. It would load it up. You would pass in this value and the spec texel, right? So the sampling sphere, this part would still be up to you, like here. But, you know, you would pass in that, which you already are. So you would pass Raycast, work. The Ray origin here is just, you know, whatever the light probe P is, I believe. So Ray origin and Ray direction. And then you would pass the spec texel. Then it would actually update the lighting in place for that thing. So really we're just calling this thing a few times and it's doing its business, right? Yeah. So I think that's more what I want. So then what it does is it does the load up of the samples, and then it does the write back of the samples. And I think I like that better because now I can sort of see what's happening easier, and I can start to optimize this routine as a whole, which I like better. And excuse me. And so this stuff here where we're using like hit normal and all that stuff, I can also then, you know, make that be more coherent with what's going on. So yeah, that seems more sane to me. That seems more sane to me. When we're actually doing this and we're doing it for Y, though, if we're loading up these, again, doing 8 at a time seems good, but maybe, again, like, maybe we'll just, to make it a little easier on ourselves, because everything was written for Y to begin with, we will just only do 4. So we'll call this twice, essentially. like that. So we'll do 1 through 4 and then 5 through 9. I'm sorry, 5. 1, 2, and 3, and then 4, right. 5, 6, 7, 8, 9. Yes, no, sorry, that's correct. 5, 6, 7, 8. 5 through 8, 1 through 4, and 5 through 8. Like this. That seems reasonable to me. And that way, yeah, we just know that the spheres are set up correctly. We have a nice little simple loop here that goes through each individual place we want to cast from, does the cast, and off we go, right? That seems fine. And then we just have to make sure this routine can work that way, right? So it's going to go ahead and load up those. I guess it doesn't really need them till the end, so we might as well just put them down here. So it loads up the S zeros, it loads up the T zeros, it does the blend, and then it writes them back out, right? That seems totally reasonable. I don't know. Yeah, so I guess for now, we'll just go ahead and do the for I loop here. On the subray. And then we'll go ahead and try to make that better later. Because this code is terrible, right? Not entirely our fault. Lookups like compute voxel radiance are bad for that, but anyway. So here's our little cheat sheet here. So for each ray, we want T ray, and that's just this, apparently. So that's good. T-ray is T-ray. Emission direction, this we already know, right? The T-hit we're pulling out there. Probe sample P, ray.P, that's just hit P. This is hit normal. Ref color is hit ref color. And emission is hit emission. So looking at here, I assume that the problem is we don't have the solution pulled out. Oh, no, we do. What's the problem there? Diffuse atlas. So we're going to have to pull out the diffuse atlas as well, which we can do here, I assume. Oh, you know what, though? I guess we just can pass those down. Let's just do that for now. There we go. So probe sample P, probe sample N, emission direction. Where is emission direction? It's up here. So what's the problem? Compute voxel rate. Oh, we just jumped over it. Might as well just grab these and put them up above here. There we go. So in this case, we need to write back the transfer PPS correctly. And I think if we just do it this way, we will. So again, this just loads them out in the opposite format. So I think that's all fine. And then we just need to do our hard-coded moondir nonsense. We just have to move that in there. And we want to figure out what our long-term strategy is for that. I don't actually know what we're going to do, but eventually we want the moon to only affect outdoor areas and stuff like that. So we're going to have to do something with that eventually anyway. But if we go ahead here and grab that out for now, we can just go ahead and put that in the Raycast for now. All right, so t-update blend is, again, just something we probably want to pull out of the solution here. So when we actually are doing the Raycast, we just grab our t-update blend then. We don't need to do the extra blends for stuff we didn't load. And then I think we're good. So here in our test caster, we can't actually do this one anymore, which is fine. That's no biggie. But I think I may just remove the test caster entirely. Should this wait? What happened there? Okay, so what we actually want here is this, right? There we go. All right, so now we've got the Raycaster going, and this is going to be a complete disaster because what's happening now is we're casting off of spheres that are not correctly they're not correctly aligned to those octahedral maps, but we're writing them as if they were, right? So we're casting rays in arbitrary directions and then writing to anywhere in the map. So obviously that's wrong. But otherwise we're fine, and this will allow us to just look at this one routine and simplify it down exactly however it needs to be. So the other thing that I would note is if we take a look at what's going on here and we look at why we need, for example, some of the most expensive stuff we're doing here is for computing the normal. Like, you can see how simple it is to compute everything else, but computing the normal is a huge pain in the butt, right? And our compute voxel irradiance at, like, that's the thing that uses it, right? Our compute voxel irradiance at is doing the lerp based on what, like, we're using that value, that hit normal, right, to look up into the octahedral map, and the octahedral map is a txty. We're only ever going to be sampling from certain of those txtys, right? Because our surface normals, there's only 6 of them that there can be, right? And so another way to look at this would just be, look, we don't actually have to do all this work. Instead, what we can do is just know that there's only 4 lookups we could possibly do, and let's just load whichever of those 4 lookups is the one we need. Right? So the tx and ty values we can just get back directly from that, I think, and avoid doing this. So I'm not going to change it now, but you know, probably the short end of the stick because it only happens at the end, but I'm just, going to note all of the places where we can improve things because we don't know how hardcore we're going to have to get on this thing. All right. So I think this should roughly do exactly the same thing as we were doing before. The only difference, like I said, is that we're not actually sending things out the octahedral map at the moment. So what I might suggest is, look, let's just actually generate noise temporarily, or not even noise. Let's just generate exact casts out from the centers, let's say, and use that just to verify that we can get everything working, right? So in here, instead of grabbing these out, so I'm going to go ahead temporarily and say we've got a v34x. It's like sample dir a, and it's this. Oops. And then a v34x that's sample dir b, and it's this. What I want to do here is just let's overwrite those, right? Let's just overwrite those entirely. So what I'd like to do is overwrite sample dir A and sample dir B with actually with voxels that with direct output directions from the voxel, right? So we want to do like this kind of thing where we just say like, all right, whatever the SY value is, we're going to use that, and then we're going to get the directions here, you know, like this, right? And we're going to stuff these in to the v34x like so. So we're gonna basically do like sample dir A gets overwritten by a direct load, and sample dir B gets overwritten by a direct load. So now we know that these things are going directly out the texels in question, right? And if we do direction from, excuse me, if we do direction from text Y, what I'd like to do here is we need to pass the OXY coefficient. I think we can get that directly from the atlas, right? So we shouldn't have to do any work there. There we go. And so now hopefully we're at least sending things out the correct direction. I don't know. So it's close. It's at least looking sort of right. We may still have some bugs in there. But remember, currently there's no jitter, right? So it's now not picking up any light that it doesn't just happen to hit with that one direction, right? But of course, yeah, it's nice and stable and everything else is fine. What I don't know, however, is if we're missing anything like with the write back, right? We may be missing something there. It's hard to say. So without the jitter to get us back to our previous lighting solution, I don't actually know if this is correct or not. We'll see. So what I'd like to do now is maybe let's pong back to the actual sphere code. And what we can do is we can make our spheres always go out the correct voxels now, right? And this code here where we've got direction from TXY and get octahedral offset, I think that can go in the math now, the layer 2, because now that we've got octahedral from unit vector and unit vector from octahedral, these could also be, these also would work because these coefficients are now just regular variables, right? They don't require you to have like an atlas pointer or anything like that. Excuse me. So if we want to update our sphere generator, that would allow us in theory to make this work properly, because now we would just make sure that the sphere data that we're outputting happens to have things aligned with those voxels properly. Let's go ahead and try that. So if I go ahead and nerf this and go to our HH sphere code, what you can see here is when we do our output sphere, you can see it outputting the sampling sphere here. I don't know where we got the idea that there was going to be 18. I guess that's just how many we were using before or something. Because like like 18 times 4 is 72, and I don't know why 72 was the number that we were doing. It's confusing, but I guess that's what we typed in, right? We typed in an 18 here for some reason, so I don't know. So when you look at what output sphere INL does, that outputs everything that we wanted, and it does it exactly the way that we want. We don't need to change that at all. So I think we can keep this exactly the same. What we will have to do is, for generate lighting pattern, we're going to need to do something different. So in here, what I would say is this can be generate like Poisson lighting pattern, and then we'll have another generate lighting pattern that's a different thing. So we'll have generate octahedral lighting pattern. And so what we want to do here is be able to output the sample directions exactly as we were doing before. And you can see here we've got a thing that like produces the bundles from the directions, right? So we probably want to make that be just a utility because we're going to want to do that in both cases. So in this case here where we're doing dir from directions, I'm assuming what we want to do is generate all the directions the same way we were generating directions before, and then use this piece of code, right? So this is like something like this. So you pass the sphere count, you pass the directions, and you pass the sphere you're trying to write to, right? The sphere array, and it just goes through and copies the directions into the spheres for you, right? And we would need ray bundles per sphere as well, in this case, like so. But otherwise, that would do it. I think. Yeah. So that seems fine. And this would do the same thing, right? Excuse me. And so all we need here is that the directions, like this stuff, we would want to do the exact same thing. I don't know what the used thing is for. We probably don't care about this at all at the moment. But we would say, all right, that's total directions. Here's the directions. We don't care about this, and we don't care about that. So we would just go through, and for each sphere, we would just like, we'll just use noise for now, right? So what we'll do is we'll say, I guess in this case too, these two values are kind of hard-coded, right? Meaning you don't actually get to choose them. So really, what happens here, sorry, not the sphere count. The sphere count it's the ray bundles per sphere that you don't get to choose, right? It has to basically be, well, no, you know what? That's not true. So we can leave it like this. What we would do is we'll just keep wrapping around, right? So that seems fine. So then what we would say is, okay, for each sphere, right, because we've got to initialize all of our spheres, right? Also, why... Okay, so this pulled the spheres out of that. All right. I don't think we care about a lot of this stuff. But anyway, so what we want to do is for each sphere... so you know what? I'm starting to get a sense for how this would work. In fact, I think I see exactly how this would work. So what we would want to do is we'd want to do exactly the same thing as we were doing in the other one. Meaning this routine actually, I think, is more or less correct, now that I think about it. It's just, it would get a little more complicated, right? So what we want to do, I think we do want to generate a blue noise sphere. But what we want to do is we want the blue noise to be evaluated only inside each individual tile. Now, the ultimate thing to do, and unfortunately, I just don't know any way you would actually do this. I'm not sure how you would actually write the algorithm to do this. I'm trying to think. But so what you would want is you would want to be able to generate you'd want to be able to generate a sphere that was a Poisson distribution exactly like we were doing. So you could literally run the exact same code, generate a Poisson sphere, and then you would just want to pull out for each sphere that you write out, you'd pull out 1 point from the evenly distributed Poisson sphere, 1 point per octahedral tile. Now the problem, because I could just write that, and that'd be it. The problem is how do you guarantee that you always have, however many spheres? Let's say you want to generate 64 spheres. How do you generate a Poisson distribution that guarantees that each octahedral tile always has 64 points in it? I don't think you can. So my suggestion would be maybe what we do is we generate the Poisson sphere, then we pull out 1 per tile, right? And we just use white noise to fill in the gaps. You know what I'm saying to you? I mean, right? I mean, that seems like the sanest thing to me. So, yeah, I think that's correct. So I guess what I would say is we probably want to do the generate Poisson lighting pattern as a thing you call. And what that does is it just returns you like the distribution. So the direct, like this thing, right? So you call it, and it does whatever random crap it's going to do here. And what does it care about? Does it care about just total direction count, probably? Yeah. So what we do here is we'd pull out this total direction count. And we'd just say, all right, so in each case, you compute the total direction count, but then, you don't do any of this stuff, right? You just call this routine, which does the Poisson distribution. So you pass total direction count to it. It just does whatever it's going to do to generate the sphere. And that's fine, and everyone loves it, and it's great, and like everyone's dancing in the streets and having a party and getting coronavirus. So then we just get the directions back by calling that function. And then in the case where we want to actually just generate the simple Poisson lighting pattern, we do the interleave directions call, which I was totally wrong. That's not the thing we probably actually want to call here, but, whatever. It's fine. So in there, we would call interleave directions after calling whatever this is, generate Poisson distribution with the total direction count. And then for our generate octahedral lighting pattern, what we would do is we would go through, right? And now what we want to do is split out. We'd want to split out by basically using this used again, probably, right? We would want to split out the... I guess we don't really need that. We can just set the things to 0, 0, 0, actually. We would gather, essentially, each individual thing by grabbing 1 point from the octahedral region we were talking about. So we would effectively do, like, all right, we go through each sphere. We still do want to do this, probably. Do we? Probably not. Probably we'd just do this. And so what we need to do is we need to like write these things out per sphere. And so when we do this, we would have to go through the ray bundles, and what we'd want to do is just kind of loop through the octagonal sets, pulling out ones that we find. So how we can do this? Well, what we want to do here is instead of just thinking of this strictly as ray bundles per sphere, what we want to do is think of it in terms of like tx, ty, right? And so, you know, these, I guess, are going to be, well, they're going to be whatever they are. But as we step through here, what we do is we'd say, after each time we record a direction, we're going to plus the tx. If the tx is greater than, and we could, you know, even have the, like, the dimension in here, right? If the tx gets up to be too high, it goes back to 1. And the ty increments, right? And the same thing happens with ty. Like, if the ty is greater than however much the max is, it goes back to 1. So we just say, like, look, the maps here, and maybe we just put in the offset separately. So maybe we just say it's an 8x8, and we use 0 based here just to be a little bit fancier, right? So we loop through, we go through pulling out bundles, and each bundle goes into subsequent slots in the map dimension, generating the octahedral lighting pattern. And so all we then need to do is figure out whether or not a particular thing falls into that region, right? And so in order to do that, we already have the function, which is like the get octahedral offset, right? So if we call get octahedral offset, is that the right thing? Yeah. So if we call get octahedral offset, get octahedral offset tells us the like the xy of this thing, whatever sample we're going to look at here, right? So I have to blow my nose for a second. And so each one of those that we pull out, we need to match against the txty that we have. So this is going to be a loop over all the directions. We're going to go ahead and get the octahedral offset of the direction. And we could cache, if we cared about how fast this thing runs, which we don't, we could cache it. But we're going to loop over each of them. We're going to get the octahedral offset and see if it maps to anywhere we actually care about. Assuming that it does, we would then go ahead and use this. So if the oxy x equals the tx, and the oxy y equals the ty, then what we would do is we would say, all right, we've found a match, and in this case, like the dir is going to be, this would be some random thing that goes off in that direction. So, you know, something like this. I might call this the match xy because this has to sort of be updated. So the match xy is actually this, right? So the direction that we actually want to pick, or maybe we'll just call this pick. So we'd loop through each thing and we'd check them. Assuming that we found one that matched, we'd pick it, right? And what we'd also want to do there, I think, is we would want to say that, you know, maybe we do it like this. And so that way we could also say, look, if the check value, if all of the check values is 0, right? Then we know that we're not going to use it. In fact, we could do that even simpler. We could just say, look, there's a magic value, you know, called used, and that's just something that can never happen, right? You can't have a normal with a 10x value. We're just going to go ahead and say that when we do that, right, the check x is going to get set to used. So we can only use each point once when we grab it out, and off we go. And here what we're going to do is say, look, we're going to just we're going to have a fill-in direction here. So when we run out of points in that particular octahedral region, we'll just fill them in with direction here. And I might say like to do perturb this, right? So give me, you know, give me something that's a little bit off from there, right? But for now, we'll actually leave it. So this would be what we're talking about. We would loop through all of the directions we have. So it would be like the dir index less than total direction count. Oops. And then our directions plus dir index would be our check vector. So this loops through every direction that we have. It looks to see whether we've used it or not. It gets where it would be in the octahedron. It looks to see whether it matches the octahedron. If it does, we use it. If it doesn't, we don't. And if we don't find anything to use, meaning we went through this entire thing and we had a break. Oh, this is in the wrong part of the thing. We would drop out of the dir check loop and just use whatever the random pick was, right? Does that make sense? Yeah. So we need to do this for, you know, to produce our bundles. And just looking at it, I think what we would probably want to do here is say, okay, I will go ahead and use the interleave because I already wrote it. And we'll just make an output directions. So here where we have directions, I'm going to do two things. I'm going to do like input directions and output directions. And output directions is going to be allocated exactly the same way. So these directions here that we've got, we now have an input and an output. And so as we go through, I just want to write to that output direction. So I'm going to call this outdir, and that's just going to start at output directions. As we go through this, we're not going to be doing this at all. So as we go through each individual sphere, we're going to actually go through 4 times the ray bundles per sphere. For each one of these, we're going to write out an outdir, right? So each time through here, when we get to this, we're going to do like, you know, outdir plus plus equals pick, like so, right? Then at the end, we're going to take the output directions. We're going to interleave those out. And I think that's roughly what I want. Now, I don't think we build this anymore. We remmed it, but I'm going to go ahead and start building it. And we now need our atlases. We need those pre-computed atlas values. So I'm going to go ahead and do that. But in the meantime, let me just finish the other things we can do there. There we go. So I'm going to call this generate octahedral. Lighting pattern here. And then I think we're good. So let me go ahead and grab the light atlas. And what we're going to do here is we're going to call that make atlas call. because that computes the values we actually need. And our voxel dim, in this case, I don't actually know how we call this. There we go. We don't care what that is, but our tile dim, we do. So the tile dim has to be 1010, I believe. Yep. So we just pass in the 1010 tile dim there, and then we can do in the direction from txty the oxy coefficient, and in here we can do the oct dim coefficient. Oh no! Wow, haven't seen that in a while. Don't know what we did wrong there. To be fair, this is like an interim. I really have to switch to the new 4-coder. It's been a long time. Just haven't gotten around to it. All right. So I think we now have our generator. I think that's roughly what I want. Again, not 100% sure, but let's give it a shot. If I call build HHsphere, we should be able to just try it. So let's say we want, 16 spheres. We want 16 ray bundles. Is that true? No. So we know we're going to do 2 ray bundles per row. And there's 8 rows. Yeah, no, it is exactly 16 ray bundles, right? Yeah. So it's 16 ray bundles, and then like, I don't know, sphere test.inl. Yeah. So this goes ahead and tries to get down to the minimum error there. And presumably this will actually output a sphere test we can actually use. Now we're gonna have to actually print like the we're gonna have to print, like, draw the sphere or something, just so we can make sure. I mean, hey, it works, but we don't actually know if it's doing the right thing. So we're gonna have to go ahead and copy that in. If I look, so I should be able to do a copy right onto that handmade code, handmade sampling spheres. And now we should actually be able to build Handmade Hero with those new sampling spheres. And we just need a way to like now inspect them, which we sort of have, but not to inspect them quite the way that we want, right? Now, if I go into the lighting code, we'll have to turn on some inspection. I can also try using the spheres, which happens in here. Oh, wait, that is using the spheres? So something must be wrong with the way we're outputting those spheres, because that means the spheres are 100% stable. Like, it's not changing the spheres at all, right? So I must have had a bug in there. Like, maybe I'm not, like, I must be picking the same things for every sphere. Does that make sense? That's all. All right. Let's go ahead and real quick rerun this. So build HHsphere 16, 16, and we want to do handmade sampling spheres. So I'm going to go ahead and rerun this. That was a mistake, obviously. We were previously literally just using this. So now it should hopefully actually pick some spheres, some of the samples, and we should get noise now. And then what we need to do is inspect these spheres by drawing them to see if they're correct. All right, so if we now recompile this, like so, what I hope to see, I don't know, is we should now see noise reappear. Although I'm not. If check is not to use oxy, if oxen check x equals used, pick equals check, and I mean, that should work, right? We're looking through all of the directions that we have, which I think should work. We're looking at any one that hasn't been used yet. We're looking to see if it equals the place we're trying to find. And if it is, we should write it. Yeah? Seems right anyway. All right. So that's much better because now we're getting like a complete disaster there, which is what I would have expected. So, or not what I would have expected, but at least it means, okay, we're getting closer to what we actually wanted here. All right, so let's take a look at those spheres. So what I want to do now is re-enable the thing where we drew the spheres, which I believe we still have. And the only question is, I guess we even did have a way to look at the different pieces of them as well. So let me go ahead and try and resurrect that code. Hopefully we didn't delete it entirely, but we may have, in which case, bad on us, because we would like to draw it. So let's take a look, see if we've still got it here. That draws our debug lines. Not really going to help us. Yeah, unfortunately, it looks like we got rid of that, maybe. Not sure why, but I'm not seeing it. Let's test the sphere. Yeah. I was hoping I just kind of saved that, you know, lying around, but doesn't look like I did. Looks like we got rid of it. Well, that's all right. So if we want to draw, it's pretty easy to do. Inside and lighting computation, I guess, would be the best way to do it. Where we can just go ahead and push debug boxes at the very end. That seems like the best thing to do. So in here, what I can do is I can go through each sphere. Do we have a way to push points? I don't know if we actually have a way to push points on there. Although I could actually just push them directly. So maybe I'll do this. So if I just push one of these on here, this should be fairly straightforward, actually. So I'll call get debug color 4 with the sphere index, and actually I guess that's all we need. So if I was to push cubes on here, what I should be able to do is push on cubes for each one. So for each sphere index, and we'll go through like however many spheres there are. So if we go to that handmade lighting spheres, we know that there'll be a sphere count here, like so. And when we go through Ray bundles, this should be, can I revert this buffer? No. So let me load that again. So when we go through here and we do the ray bundles per sphere, here's the bundle index. And for each bundle, I'm going to go for each ray. So that would draw all of our lighting spheres. And all we need to do now is extract the P and the radius. The radius is just a known quantity. It's how big we want the points to be when we're drawing them. So that's not a particularly big deal. So all we really need to do is extract that P. So what we want to do here is say, like, all right, whatever the sampling spheres are, for a particular sphere index, I then need to get the sampling direction for whatever bundle I'm on, right? Oops, sorry, sample direction for whichever bundle I'm on. And then I just use the ray index as the component. If I use that, I should be able to draw all of the spheres. And I just need that white texture because we don't actually want to put any texture on it. We just want it to be solid. Where's the if? Oops. Thank you, compiler. All right. And so now what we need is we need to place that somewhere and size it. You can see it's there, right? I mean, that's the actual thing. So what we now need to do is place that somewhere and make it a little larger just so we can see it easily. So I think those radii that's a little bit too much. So we'll go ahead and drop that down a little bit. And then what I want to do is just take the Z and I'm just going to lift it up a few meters so it's in a place that's easier to see, right? All right, so there's our sampling spheres. I don't know that I'm drawing it correctly yet, but whoa. What the heck? Wow. That's total nonsense. All right, so now that we've got that, I should be able to go debug our HH sphere because we should be able to figure out what we're doing wrong and you know, make the stuff work properly. Oh. That's good. We slammed that 10 in there. Do you think that might have something to do with it? Yeah. Before we overwrite the X component with 10, we may want to copy the value out. That was a bit of a mistake. All right. So hopefully now we can take a look at these spheres, see if they make any sense. I don't know if they will or not, but we'll see. And then we can try and go from there. So let's go ahead and generate our sphere. Let's recompile the game so that now it's using that sphere dataset that we just generated, hopefully without the weird bug in it. And now I'll run the game. And now we can inspect like our sphere. So it at least looks like a sphere. So, you know, I think that's a plus. The only question I have now is we kind of need to now have some way of seeing whether or not these things are correctly like lined up, right? Because we don't actually know right now if they're if they're actually in the octahedrons that we think they should be. So what I want to do, you can see, you know, from the colors that the colors look reasonably distributed, but you know, that's telling us for each sphere. So what I want to do now is say, look, let's actually look at the bundle index ray index, and let's see if we can make the debug color line up with that instead. So what I'm going to do is I'm going to say, look, for the debug color, I want to get the bundle index plus the ray index. So like 4 times bundle index plus ray index, right? And now I should see colors clustering around the sphere, right? So if we look at where each cluster is, each color should sort of be a region of the sphere. And that does look like what's happening, right? So that does look pretty good. Like, I think that's probably, you could make a good argument that that's correct. So I think we're in good shape now, right? Now, it looks like we still got some bugs here. So I think our Raycast routine is still a little bit buggy. But I'm going to go ahead and turn off the sphere render temporarily. And I'm going to go look at the Raycast routine and see if I can clean that up a little bit now. Although maybe we should save that for tomorrow. All right, so here's us hopping around, and you can see the lighting sort of works, but it looks like there's still some bugs, right? It looks like maybe there's some bugs in the way that it's working at the moment, right? In other news, if we take a look at the profile, we can see we're hovering around our 30 frames a second pretty easily there, right? Not able to get down into the 60 frames a second, but we're in much better shape. So. All right, so now we got to figure out what exactly is going on there. Why are we getting that weird behavior? So here's our sphere indices, bundle indices. We drew those looked correct. So we know we should be able to loop over these things pretty much the way that they're being looped over now. Let me just take a quick look, and then we'll save any heavy debugging for tomorrow. So I won't dive too far into it, but I just want to take a look. So yeah. After we're doing our Raycast here, you can see us doing our transfer PPS. Let's see, where do we pull out the sampling sphere? So let's make sure. Where do we get that sphere? So this seems right. We're masking out there. We're taking sample directions here. I guess, are we making sure we're filled as much as we think we should be? So I might say, hey, double check that the light sampling ray bundles per sphere, assert that this never goes above that, right? Because we don't ever want that to, we don't want that to overwrite that buffer, right? So we want to make sure that that's in bounds. And similarly, we should assert this one as well. And that just means, let's make sure we're not sampling off of the array or something like that. It's just basic bounds checking and get in place there. Okay. So assuming we have the basic bounds checking in place, now let's just make sure, okay, our spec texels, we're going in X, which is what we would expect. We're looping over the tile dim Y, and that seems right. So this here was wrong, incidentally, because that +1, oh no, it wasn't. That was right. That's fine. So yeah, I don't see anything obviously busted there. So I think that's fine. I do think my transfer PPS code may be wrong, and we should look at that real quick, because that was another big change we made. So looking at the Raycast here, that's probably fine, right? This looks like sample durs have probably come out of the right place. They're the ones for this particular row. And the spec texel's probably right there. So let's take a look at the Raycast part of things here. So really it's this part here that we're looking at. So if you look at what happens for our transfer PPS, we're producing RGB, 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 RGB. And I think this should work properly. Like, we're loading the spec texels, that's RGB, RGB, RGB. So that's loading 3 Oh. But that's just wrong. No, it's not. No, it's not. That's really RGBR, GBRG, BRGB, right? And so is this. So those should both load 4 wide times 3 or 3 times 4 worth of ops. We load in the blend values and we blend them together. Oh, and we never change those variables. So yeah, I mean, that could have been our only bug, but it's doubtful. All right, but that looks much more like it, right? All right. So I think that's a good place to end it for today. Again, we're not really done at all with what we want to do to this routine, but at least now we're operating in order, and we're not like calling a bunch of random crap we don't need to. Because since we compute the sampling spheres, there's no reason for us not to know exactly where to write for each sampling sphere. And this way we also know we update the map relatively uniformly, which also I think is a good idea. So every texel gets a refresh value once per frame, which I like, right? So I think that's good. Let's go ahead and go to brief Q&A. When will programming return? I don't know. Like at some point, I may do a real one. I just need to rehearse one first at some point, and so I can. It's hard to do it and not make mistakes in the code and remember to say weird stuff. So at some point, I'll try to record one and put it up. So you don't have to use static. So here's what happens. When you don't mark a function as static, because I assume that's what we're talking about, because I don't really use static much else otherwise, because the only other time you would use it is for like a global variable, maybe. I don't use static for pretty much ever inside inside actual to have local persistent variables. I don't ever use it for that because it doesn't really work very well with multi-threading usually. So it's just I'm out of the habit, right? But the reason that I use static is because anytime you don't use static, the function is by default externable. So it goes into the linker at that point. And the linker is notoriously like the slowest part of the compilation process typically. Especially if you're not doing random crap like weird templates and huge amounts of header files. So the problem is like, I just don't ever want to put more stuff in the linker than I have to. So it's only for optimizing build times. You don't need to do it to make your code work because it doesn't matter, right? So that's what I would say. I would heavily encourage you to use it because it does help build times. But I would say if you don't use it, there's nothing. The only thing that's the problem is the linker can get slower. Largely because linkers seem to be written very poorly. Is a 3D shear transformation useful in graphics programming for games? How do you construct a 4x4 shear matrix? So the second part of your question is easy. The first part of your question is hard. Let me try to take the hard part first. Is it useful? I mean, it's hard to say. It can be. It can sometimes help your artists get squash and stretch, you know? It's just, the problem with it is it causes a lot of headaches. You can no longer treat things as just a position in a quaternion, right? So it's no longer V3, V4. You now have to actually have a scale shear addenda to that. And so, you know, it's hard to say whether it's useful. It may or may not be useful is probably the best answer I can give. It really depends on what you're doing and what your animation system has for support for like mesh morphing and whether or not you can attack those kind of squash and stretch animation problems in a different way, right? So I really just couldn't tell you. It can be useful, but it really depends on what you're doing. It may just be overcomplicating things and you don't need it. So that's just a really hard question. The easy part of your question, which is how to construct it, is, well, all you have to do is just when you make the matrix, don't try to make the basis vectors be orthogonal. That's it. So if you imagine, let me just draw it for you here. So the important thing to remember, and we've talked about this a lot on Handmade Hero, so go back and look at matrix stuff if you don't understand what I'm saying here. But again, if you just always remember the fundamental construction for an object placement matrix, it should be obvious how you create a shear matrix. So I'm just going to reiterate that again. Here's your matrix. And if you're a longtime Handmade Hero viewer, you should be able to look at this bag of numbers, which is a 4x4 matrix here, right? And you should be able to say, if this is something that takes a object and places it in the world, which is where you'd be doing your shears or whatever, you should be able to pull out for me exactly what that object's X, Y, and Z axes are and what its origin is, right? And so what you would expect to see is this down here, MNOP would be, and if I'll draw it over here, would be 0, 0, 0, 1, right? Because this is the part of the matrix that deals with the W parameter of your input. And so it's not really participating in placing this object unless you're doing things like trying to move things into the output W, which is for, you know, perspective transforms and things like that. So you're looking at this bag of 12 numbers right here. Where's the position? All right. Everyone who watches Handmade Hero regularly should be able to pull this out. If you don't, I'm going to have to go programming on you again. So it's right here, right? This is the position. This right here is the vector that is the position of the object that you're placing. So it's a px, py, pz, right? Is these three. And then where's the x, y, and z axes of this object? Okay? It's here, here, and here. So that means we have our x-axis x, our x-axis y, our x-axis z, our y-axis x, our y-axis y, and our y-axis z, our z-axis x, our z-axis y, our z-axis z. Okay? And so now we can see that for any bag of 4x4 numbers you're giving us, if you're telling us, hey, this is an object transform, we can immediately tell you that these are the parameters for it. right? So that tells us exactly, just by pulling the numbers out, no work on the numbers, exactly this. Here's the origin, here's the y-axis, x-axis, z-axis. They are literally these right here. All right? So if you know that, now you should be able to make your shear matrix trivially. All you have to do is, well, a shear matrix doesn't move anybody, right? So the p values are just 0, 0, 0. And the bottom obviously is 0, 0, 1, right? So we can start off there because we're not trying to place the thing anywhere. We're just trying to shear it. So then we could say, well, what kind of shear are we trying to do, right? And I guess I don't know what kind of shear you're trying to do, but let's say you were trying to shear the y-axis. So what you want to do is you want it to kind of look more like that, right? So you're shearing this over. So what you're going to do there is just say, okay, my z-axis and my x-axis are not going to change. So I'm going to put my x-axis in here, right, which is 1, 0, 0. That's just, the x-axis unchanged. My y-axis I'm going to shear, so we'll leave that out for now. And the z-axis is also going to be unchanged, right? So now I want my sheared y-axis. Well, what would a sheared y-axis look like? Well, if I wanted to produce a thing that, sheared like that, then my y-axis should just be set to, I don't know, 1, 1. Let's say that would be that point there, right? That would shear me over by 1. Okay? And again, you can just conceptualize it by saying, what did you want these to do, right? Maybe you wanted to shear in y as well, in which case maybe you would put a 1, a 1 there, right? I don't know. I don't know what kind of shear you're trying to do, right? But however much, for this, for example, if you just wanted to do a y shear, however much y shear you wanted would go right there, right? And we know that because this is the y-axis. So if you want to do an x shear on the y-axis, right, or a y shear, I don't know why you describe these things. But if you want to shear your y in the x direction, then that's just that value. And we know that because that's where the y-axis goes, right? So does that make sense? Okay, cool. A couple other questions here. Let me see. Which kind of light does Handmade Heroes support? Did I assume right it support any as long as you put light correctly? Maybe moonlight can be a planar light put over rooms marked as outside. Yes, we certainly can. We pretty much don't have any restrictions on the light at the moment. We could just put anything we can evaluate for a raycast can be in there. So if we want to, like you say, we could totally just put a fake light that's like a roof over outdoor rooms, and it just says, if you hit this thing, compute a moonlight. We could totally do that. And that may very well be what we do. We don't really have any need to do that until we actually have everything else correct. But putting in types of lights, is pretty much free, because since we're using raycasting, it means that anything you can compute a raycast for, which is literally all lights that exist, period, pretty much, we can do. Could you check how much slower the build is if you define internal to nothing? I can, although it's probably not a particularly good check, because Handmade Heroes codebase is fairly small, so I wouldn't really expect it to save that much time on a very small codebase, right? Because there's just not that many functions. So we certainly can take a look at it. If I go here and run the builds, we can take a look at how long that takes, and see if that's a consistent number, 4.887. And what we may want to do too is say, look, the debug build is the one that's going to be fastest, and would possibly be the one to look at there. So if I do a build for debug and look at how much time is, that's 2.203. 2.406, 2.203, right? So it's going to be kind of hard to measure something that small. But it's in the 2.2 to 2.3 area, right? Yeah, so I can go and take a look at internal, and I can try, I don't know if we'll compile without that, but we can try. So it looks like, yeah, the problem there is we're getting some unresolved externals there. But that's really only cut at HH sphere, so I could get rid of that. But it looks like I said, Handmade code isn't that big, so I wouldn't expect this to really make a difference here. And I don't think it really does. Let's try that again. So that's, you know, roughly 2 seconds, and now I'll put it in, and my assumption is, you know, it'll basically be the same. I mean, you know, we're not even measuring, I think. So yeah, I mean, even there, I guess it is slightly faster. Looks like it's fairly consistently slightly faster, but again, like, not in a meaningful way. So, you know, again, with a code base of this size, I don't know that you'd really care about it. But it does look like it's slightly slower, oddly enough. I wouldn't necessarily have thought that, but it does look like it's pretty consistently slightly slower, right? Looking at the release build, my assumption is that the percentage of the time that it would take there would be even less. I could be wrong about that. But, you know, if we take a look at, that's just because release builds tend to be longer, so the amount of time it's doing resolving the names would take up less of the time. But again, so looking at like a 4.3 to 4.4 range in there, and then if I go ahead and get rid of that, and I do a build, we can see if it's any different. And looks like we're failing there, though. With an unresolved symbol mem copy there. So hold on a second. So I'm not really sure why we're getting that mem copy. We don't call mem copy. So I'm not sure why that would actually, that's just in the preprocessor. So it looks like checksum of, for whatever reason, if we call checksum of, here we're getting, that's actually generating a mem copy for this, I would assume. And I don't know why. It may just be because... okay. So... it may just be because since it can't see it, or since it thinks it's external... Gosh, I don't really know why it's doing that, though. Let me just see what happens. I don't really know. I don't know why it's outputting that. You got me. The compiler is putting it in, like we're not calling it, but for some reason, and I would have to investigate more closely. So I don't know exactly why it's doing that. But for some reason, it looks like in the optimized build, if you don't include that, it can't actually do the build because it inserts a spurious mem copy. And I don't know why. So I guess that's another reason to always use it. No, it's not because we rem something out. That's just the sphere build, and we don't need to do that. So I don't know. That's not a reason I would think. So as you can see, it does actually even get slower even for our code base, which is a little bit surprising, but that's the case. And so, yeah, I don't know how much slower the release build gets, though, because it was hard to tell since it can't complete it without that. All right, let's go ahead and wrap it up. Thank you, everyone, for joining me for those that are Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow on the series at home, you can always go to handmadehero.org and pre-order the game, and it comes with the source code so you can do your own experiments with it. Maybe you'd like to try optimizing our lighting code, which is what we're going to start on tomorrow. You can see if you can make a dent in it. I think there's a lot of fat in there we can start to trim. So we'll go ahead and do that. Hope to see you back here tomorrow for that. Till then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.